Manna in the house. We're doing section 8 in Calculus, chapter 7. Okay. All right, we're going to do improper integrals, which basically means integrals where one of the limits of integration is infinity. So, first thing, if we take the integral from a to infinity of some function, it's really not proper to use infinity as a limit of integration because it's not a number. So what we do is we say, technically what this is the limit as t approaches infinity of the integral from a to t of f of x dx. So basically what you do is you evaluate the integral from a to t, and then you apply the limit, and then you can get the value of that integral. So everybody get to page 530 in your textbook so you can see what's going on here. All right, the next integral is if we start from negative infinity and go to some point b of f of x. And same thing, we're just going to take the integral as t approaches negative infinity of the integral from t to b of f of x dx. Now, if we have infinite limits on both sides, then you have to do two different integrals. We're going to do the integral from, as t approaches infinity, from a to t of f of x dx, and then we go the integral then the limit as t approaches negative infinity of the integral from t to a of f of x dx. So check out figure 3 on page 531, and you're going to see what that means to have an infinite area that we're calculating a finite sum of. Now, it's a little bit strange to think that you could have an infinite area, or put it like this, okay, you have a finite area that goes on forever. But if you think about 1/3, equals 0.3 repeating. So what does that mean? Well, that equals 3/10 plus, 3/10. All right, that was bugging me. 3/10 plus 3/100 plus 3/1000 plus, and it keeps on going forever and ever. So even though we have an infinite number of values that we're counting up, it equals a finite value, 1/3. So there really is no problem with having a limit or an integral to infinity that's going to end up being a finite value. Okay. Okay, next thing, sometimes these integrals do end up being infinite. So if you have an integral from a to infinity, or an integral from negative infinity to b, or an integral from negative infinity to infinity, if the limit is a finite value, you get one single value for the entire integral, that's called convergent. The integral would be said to be convergent. If the limit's infinite, then you would say that the integral is divergent. So convergent, it converges to a single value. Divergent means it diverges. There's no single value that you're going to be able to calculate for the area. So if you want to see the diagrams to illustrate that, check out figure 4 that shows convergence, and figure 5 shows divergence. So the way I look at it is on a, like a physical analogy of it, convergence is if you have a really thick oil and you put it in a bucket that has a tiny pinhole in it. But the oil is so thick, it can't get through the pinhole. So that's like this convergent. You have a finite area because that yellow oil can't seep through the tiny little hole in the curve, between the curve and the x-axis. But then if you look at the figure 5, you see divergence where the oil isn't thick enough or the hole is too big to hold the oil and it's going to seep out and you can't measure it. You have to keep pouring more and more oil in. So that's divergence, and it's infinite. And everyone loves my analogies, of course. Okay. All right, so next, we're going to have integrals with vertical asymptotes. So everybody check out page 534. If we have a vertical asymptote on the right side of the function at x equals b, then the integral from a to b of fx dx, well, b doesn't actually exist. So you have to say it's the limit as t approaches b from the left of the integral from a to t of fx dx. So now we're basically going from a finite point A to some asymptote on the right side that's going to be the left side of B. So that's it. Now, if our asymptote's on the left side, like figure 8, then the integral is going to be the limit as t approaches A from the right of the integral from t to b. So the limit as t approaches a from the right of the integral of t to b of fx dx. Okay, and now the third situation is if the vertical asymptote is right in the center. So a and b are defined, but c is not. Then you're just going to go the integral from a to c, which would be the limit here where you're taking the limit as t approaches c from the left, plus the integral from c to b where you're doing this one. So basically the center one is a combination of the first two. So these are similar too. Sometimes you're going to get divergence and sometimes you're going to get convergence. So you just have to work out the integrals. Oh yeah, and notice C could be deceptive because if you don't realize you've got an asymptote right in the middle and you just go, oh, we're just going to go right from A to B and totally ignore the fact that you have a C here, then you could be in trouble. And if you do that on the test, of course, hackage will ensue. Okay, hackage will ensue. Okay, now, the third general principle here in this lesson is the comparison theorem. So everybody get to page 536 and check out figure 12. All right, we have a situation where we have two functions, f and g. Now we may know something about f or g, but we don't know everything about both f and g. Now the one thing that we do know is they both have to be continuous, and f is always going to be greater than or equal to g. In other words, the f function will always be above the g function for all values in the interval that we're interested in, which means x is greater than or equal to some starting point a. Now, there is no ending point, there's no b here because that's going to be infinity. So now, if I want to know, or if I find out that the integral from a to infinity of f of x is convergent, then that guarantees me that the integral from a to infinity of g of x will be convergent. Because if f of x is above g of x, and f of x converges, then g of x for sure converges. So if the hole in the f function is small enough that it's going to hold the oil, and the g function, the hole is even smaller, then for sure the g function has to hold the oil. Now, on the other hand, if we find out that the integral from a to infinity of g of x is divergent, in other words, the g function, the hole is so big that the oil is leaking out, then the f function is for sure divergent. The hole in the f function is bigger than the hole in the g function, so if the hole in the g function is big enough that oil is going to be leaking, then oil will for sure be leaking in the bigger hole of the f function. Okay, now, there's two more situations that students often mess up. So I want to show you these holes not to step in. Okay, if you find out that f is divergent, then you have no conclusion for g. Because the fact that f is bigger, it's divergent. Well, g might be divergent also, or since it's smaller than f of x, it could be convergent. So you don't know. If the top function is divergent, no conclusion. Same thing, if the bottom function is convergent, you don't know a thing about the top function. It might be convergent too, it might not be. So what you need to make a valid conclusion is the top function is convergent, which means the bottom function is also convergent, or the bottom function's divergent, which means the top also has to be divergent. But if the top is divergent, we don't know anything, and if the bottom is convergent, we don't know anything. So that's it. All right, now, the only other thing we have to do is actually work out some problems. So in the interest of getting this fascinating program finished in a reasonable amount of time, we're just going to arm wave our way through the examples in the book. So everybody get to page 531. Okay. We'll just go with the blank screen to highlight my beautiful accents. Okay, so check out page 531, example 1. So we want to know if the integral from 1 to infinity of 1 over x dx is convergent or divergent. So all you do is you take the limit as t approaches infinity of the integral from 1 to t of 1 over x dx. So we do that integral with t in there. So that's going to be the limit as t approaches infinity of natural log absolute value of x from 1 to t. Now, when you you plug in t, you plug in 1. Now natural log of 1 is 0, of course. So you end up with the limit as t approaches infinity of natural log t. Well, that's going to be infinity. That means this function diverges, or the hole is so large that the oil is going to flow out. Okay. Now, if we do the same thing with the integral from 1 to infinity of 1 over x squared dx, we find out that we're going to get a finite area, so that means that integral converges. So we're happy about that. Okay, so now, example 2, we're going to evaluate the integral from negative infinity to 0 of x e to the x dx. So, so basically what we have to do is we can't actually just apply the limit of negative infinity. We do the integral from t to 0 of x e to the x dx, and then we apply the limit as t approaches negative infinity. So clearly we need to do integration by parts with x e to the x dx. So we say let u equal x, let dv equal e to the x dx. So then du is going to be dx and v is going to be e to the x. The integral of e to the x is e to the x. So now we go integral from t to 0 of uv minus v du. So that's minus the integral t to 0 of e to the x dx. So that gives us t e to the t minus 1 plus e to the t. Okay, so we evaluate the limit as t approaches negative infinity. And notice you've got negative of negative infinity times e to the negative infinity. So that basically means we've got infinity times 0. And we don't know what that is. So we have to apply L'Hopital's rule, and we end up with that limit equaling 0. So when we apply the limit to the minus 1, we end up with minus 1. So the entire area is negative 1. So that is convergent. No, class isn't out yet. Don't be thinking that. Okay. So, yeah, that is convergent, and your area is negative 1. Okay, example 3. Now we've got the integral from negative infinity to infinity. So we're going to have to do two different limits here. We're going to take the limit as t approaches infinity of the integral from 0 to t, and then we're going to take the limit as t approaches negative infinity of the integral from t to 0. Now, 0 just happens to be an arbitrary value. It doesn't really matter. 0 is just a handy thing to pick, so that's why we're picking 0. So when you do the first limit as t approaches infinity, you end up with inverse tangent x, which of course you all remember that integral of dx over 1 plus x squared is inverse tangent. So that's going to end up being the limit as t approaches infinity of inverse tangent, which you know is the asymptote at pi over 2. That's happy. Okay, now we go to the other side, and we end up finding out that that limit is going to also approach pi over 2. So both the areas end up being pi over 2. You add pi over 2 plus pi over 2, you get pi. So that's it. It converges. Now, if one side were to converge and the other side diverges, then the entire integral would diverge. Okay, now, example 4 is saying what value of p is the integral from 1 to infinity of 1 over x to the p going to be convergent. So in other words, we just found out that the integral from 1 to infinity of 1 over x diverges, but that the integral from 1 to infinity of 1 over x squared converges. So is there some pattern that we can say for p that, that it converges or diverges? So notice what they find out is, if p is greater than 1, then you get convergence. But if p is less than or equal to 1, then you get divergence. So the integral from 1 to infinity of 1 over x, or 1 over x to the 0.9, or 1 over x to the 0.8, or anything less than that, that's going to diverge. But if you go limit, or the integral from 1 to infinity of 1 over x to the 1.01, or x to the 1.5, or x to the 2, or x to the 3, or x to the 4, or x to the 10, then that's going to converge. So if p is greater than 1, we get convergence. If p is less than or equal to 1, we get divergence. Okay, so cruising onward. Example 5 is example the type 2 integral, where we've got an asymptote in between, or not in between, no, I'm sorry. We've got an asymptote at x equals 2. So when we want the integral from 2 to 5 of 1 over square root of x minus 2, we can't take the limit, we can't just plug 2 in because it's undefined at 2. So that means we're going, the limit as t approaches 2 from the right of the integral of from t to 5 of dx over the square root of x minus 2. So we do our integration, and we end up with 2 times square root of x minus 2, evaluate from t to 5. And so that's going to be limit as t approaches t approaches 2 from the plus of 2 square root of 3 minus the square root of t minus 2. So if you take 2, if it's as close to 2 as possible, well then that radical gets close to 0, so the entire limit gets to 2 square root of 3. So that's it. It's really pretty simple. You just do the integration and then do a limit. So these problems are simpler integrations than what we've been doing, and then you just have to do a limit problem at the end of it. Notice example 6. We're trying to find out if the integral from 0 to pi over 2 of secant x dx converges or diverges. So all you do is you know that secant is undefined at pi over 2, because the secant of pi over 2 is the same thing as 1 over cosine of pi over 2, and cosine of pi over 2 is 0. So that means it's an improper integral, but it might converge anyway. So let's check it out. So we go the integral, the limit as t approaches pi over 2 from the left of the integral from 0 to t of secant x dx, and we all remember that the integral of secant x dx is natural log secant x plus tangent x. So that means we just plug in the t, we plug in the 0, and we let t approach pi over 2. Now, tangent of pi over 2 is also infinity. So this thing diverges. So that's it. It's infinity. We quit. Okay, then example 7. We're going the integral from 0 to 3 of dx over x minus 1. Evaluated if possible. That's kind of ominous. So let's check that out. So we have to go, we realize that x equals 1 is, the function's undefined at x equals 1. So you can't just go from 0 to 3. You have to go from 0 to 1 and then 1 to 3. Well, you really can't go from 0 to 1. You have to go from 0 to almost 1. And then you can't go from 1 to 3. You have to go from just barely past 1 to 3. But the thing we find out is when we do the first part of that, it's divergent. So if the first part's divergent, there's no sense even wasting time with the second part, because even if it does converge, the entire integral will diverge. So if one part of it is divergent, then it's quitting time. Okay, and notice this warning. If you just merrily saunter on through the integral, without realizing that there's discontinuity in between the limits, then you're screwed. Okay. Now, example 8, the integral from 0 to 1 of natural log x dx. Now, you know that natural log x is undefined at 0, so we have to do the limit as t approaches 0 from the right of the integral from t to 1 natural log x. So that ends up being a little bit of a nasty integral. You have to remember your integration by parts. And so that comes out to be negative t natural log t minus 1 plus t. Now, we need L'Hopital in order to evaluate negative t natural log t. So when you take the derivative of top and the bottom, you end up with 0. And so the entire thing does diverge, and you end up with an area of 1 below the x-axis. So, and there you are in figure 11, that shows that. So the hole there between the function and the y-axis is small enough to hold the oil in. Okay, now, the comparison theorem is demonstrated here in example 9. We need to show that the integral from 0 to infinity of e to the negative x squared dx is convergent. So what you do is you say, we have no idea what the integral of e to the negative x squared is. So what we're going to do is we're going to take the integral from 0 to 1 of e to the negative x squared dx and the integral from 1 to infinity of e to the negative x squared dx, and then find out that that this limit ends up being e to the negative 1 minus e to the negative t. And so as t approaches infinity, that e to the negative t approaches 0, so the entire integral converges to e to the negative 1. Now, this isn't e to the negative x squared, this is e to the negative x, but we know e to the negative x is underneath the, I'm sorry, it's not underneath, it's above the e to the negative x squared. So notice figure 13, the blue curve is above the red curve as we go out to infinity. So we just found out that the blue curve converges. So that means even though we can't evaluate the integral of e to the negative x squared, we know that the red curve has to converge because the integral that we do know converges, and it's smaller. The e to the negative x squared is actually a smaller hole than e to the negative x. Okay, that's basically it. Now you can see what they're doing with example 10 is you don't even have to have really a related function. They're taking the integral from 1 to infinity of 1 plus e to the negative x over x. You know that that's greater than 1 over x, and you know 1 over x is divergent, so that means this big, hairy 1 plus e to the negative x over x also has to be divergent. So that's it. Have fun with these.